The title of this talk is Planning Under Uncertainty in Safety Critical Systems. So the premise of automated planning is to use predictions of the effects of different actions in order to execute good action sequences autonomously. So the idea being that if we can model action effects, either using data or using expert knowledge like physics, then we can use those models to plan action sequences that optimize different objectives. This is incredibly impactful in applications like robots and vehicles, from road vehicles to rotorcraft and spacecraft. It is also useful in a bunch of other applications, from energy, finance, healthcare, manufacturing, and games. So in many of the systems I just mentioned, bad planning can be devastating. Two systems that I got to look at during my time in my PhD were autonomous vehicles and energy systems. In autonomous vehicles, like interplanetary like rovers or vehicles that find themselves on the roads today, bad planning can lead to loss of missions or loss of life. In energy systems, like energy generation, management, and mitigation systems, failure can lead to catastrophic ecological disaster. And as such, the focus of my research has been on planning safely. Now, to plan safely, oftentimes you have to consider uncertainty. And in this talk, I'll focus around 3 different modes of uncertainty. So really briefly, they're outcome uncertainty, state uncertainty, and objective uncertainty. Outcome uncertainty describes when taking the same action from the same environment state can yield multiple different outcomes. So throughout this talk, I'll use circles to denote states and squares to denote actions. You might get outcome uncertainty from things like imperfect actuation, when maybe your motors don't do exactly what they're told, or your physics isn't exact in such a way that you might get a distribution around possible things that can happen. You might get outcome uncertainty from environmental randomness or from the actions of other agents. One system in which all these 3 are present is autonomous driving. So in autonomous driving, you often want to plan trajectories to be robust to these different sources of outcome uncertainty. The second mode of uncertainty we'll talk about is state uncertainty. So state uncertainty describes when an agent isn't exactly sure about the state of the environment that it might be in, and therefore must plan using beliefs over possible states that it could be in. This comes from imperfect information, which can come from things like noisy sensors, occlusions that occlude parts of the environment or part of the information that you might need to make decisions, or things like uncertainty about the intent of others. So in autonomous driving, you'll have occlusions, but you might also be uncertain about maybe the level of cooperation of other vehicles as you're trying to do something like merge. Finally, we'll talk about objective uncertainty. So objective uncertainty describes when an agent is uncertain about its precise goals to optimize. And oftentimes, agents can overcome outcome uncertainty by using data of, quote unquote, how experts made decisions in similar settings. So again, in something like autonomous driving, you might come into scenarios that you haven't necessarily planned against, but you may be able to use data in some data set that you collected offline to guide how you do your decision making in those scenarios. And here, experts is in quotes, because it's not all the time that those data sets represent the best action. So I'm sure many of us have been in cars with like less than great drivers. The actions of those drivers might make their way into data sets. So with these modes of uncertainty in mind, the question I was asking my research is, how can we impose runtime safety while planning under varied modes of uncertainty, and specifically in very large problems? And I want to acknowledge that there is a long history of research around this question, and I'm focused on addressing some specific challenges. So one of those challenges is that in large planning problems, it can be extremely difficult to find good solutions during runtime, leading to breakdown in safety. To address this, the solutions I'll use are reducing the size of the problem with hierarchical decomposition. So hierarchical decomposition allows us to break down very large problems into solvable subproblems, and allows us to integrate different tools for planning at different levels, at different points in the hierarchy for those problems. So for example, in autonomous driving and also in autonomous mobile robots dating back 50 years, a good hierarchy would be to do high-level route planning, mid-level decision-making, low-level motion planning, and lowest-level feedback control. again, this allows us to use multiple layers of fail-safes and insert expert knowledge where available, but also it allows for explainability, which could be nice in building trust in autonomous systems. A second or another challenge that arises when trying to do decision-making under uncertainty is that methods for planning under specifically high degrees of uncertainty require searching for often the right objectives that result in safe outcomes. Our solution is that we want to be able to specify those actual like safe sets. We want to specify and find ways to satisfy those constraints, and specifically under uncertainty. So rather than like tooling with our objective to get safety out, we want to be able to specify our uncertainty and get safe solutions. Specify our constraints and get safe solutions in a lot of uncertainty. Reasoning and trying to satisfy constraints explicitly allows us to, well, specify safety mathematically as something that can't be violated, like, for example, to avoid collisions or to satisfy minimum success probabilities for trajectories. And once we specify the constraints, there are entire fields devoted to tools to help satisfy them, where specifically in our talk, we're focused on doing this under uncertainty. So with these techniques in mind, my three contributions are as follows. In our first contribution, which we presented at the Conference on Robotics and Automation last year, we learned a hierarchical controller for safer imitation learning, and I'll go into what that is. In our second contribution, which we presented at the Conference on Automated Planning and Scheduling last year, we imposed constraints for safe planning in continuous, partially observable Markov decision processes, which are models for handling both outcome and state uncertainty. In our third contribution, which is currently under review for this year's Conference on Robotics and Automation, we use hierarchies to scale planning in large constrained POMDPs. This chart outlines how each of those contributions uses either hierarchies or constraints to address safety in either outcome, state, or objective uncertainty. And with that, we'll go into our first contribution, which uses hierarchies to improve safety under objective uncertainty. So in my thesis, optimal decision-making under outcome uncertainty is handled using Markov decision processes. So a Markov decision process is defined by states that an agent can be in, actions it can take, transition models that capture the different probabilities of different state outcomes given actions, and reward models which are used to capture the objectives. Optimal policies and MDPs find the best actions from every state that optimize reward over time. For example, we might consider a canonical problem of navigating a robot to a goal state while avoiding a penalty state. States might be the position of the robot, these cells 1 through 11. Actions might be going up, down, left, or right. Rewards encode, high rewards for getting to the objective and bad penalties for getting to that penalty state. And transitions encode all of the conditional probabilities that might come up, as in this case, from actuation, imperfect actuation. So for example, in this case, taking just the up action from state 1 might not always guarantee that we get to state 5. We might get to state 5 with a 90% probability, and with a 10% probability, we might accidentally end up in state 2. The optimal policy would account for all of this information and give us the best set of actions we can take. In these lower right states, the best action that we can take is actually to go left instead of going up, so that we could avoid the small chance that we might end up in that penalty state. So MDPs are how we'll handle outcome uncertainty.
Sorry, what's the gray square?
It's just it's square you can't go in. It's just a.
I think the policy could go that way.
Yeah, so the policy is to go that way in 6, but nothing will happen. So 90% of the time, nothing happens. Maybe some other small percent of the time, we go up or down. No percent of the time do we go backwards. So it's just to go left, keep bashing yourself at the wall until you just so you could avoid that bad state. So in my thesis, objective uncertainty, on the other hand, is treated using imitation learning. So imitation learning has the goal of learning objectives and decision-making policies that go with those objectives that mimic, again, quote unquote, expert behavior that you might see in data. There's 3 common regimes for imitation learning. Even though my contributions in one of them, I'll just briefly overview all 3. In the data-only regime, as it might suggest, you only have access to that data that you've collected offline, to learn a policy that you want to use online. So the pro of this is it could be relatively cheap to just go and collect a lot of data. The big con of this is that this can be inaccurate, especially as you get to states online that you've maybe never seen in your data set. You could get cascading errors. One way to address this is by asking a queryable expert what they might do in those situations. So you can overcome that those inaccuracy errors and cascading errors. But one con of this is that it's really expensive to have someone maybe overseeing operations that should be autonomous. The third regime and the regime we're in for our contribution is the simulator regime, where you don't have access to a queryable expert, but you do have access to a simulator that you can ask, you can query with different actions to get counterfactuals of what might have happened. So the con is that, or the pro is that this is still relatively cheap and overcomes the inaccuracies of data only. But a big con here is that this could lead to modeling errors, especially as simulators don't necessarily often reflect everything that might happen in real life. So that's just a big con of this whole this whole regime. There's other work that's trying to address this. I'm overlooking that in this work. So imitation learning in general tries to learn policies whose resulting trajectories match the underlying data distributions. In the simulator setting, one way of doing this is by using adversaries. So in adversarial imitation learning, we're learning policies while also learning how to discriminate between trajectories that came from the data and the trajectories that we're generating. So an adversarial imitation learning objective, for example, would say to learn a discriminator to tell those trajectories apart, while also learning policies to fool that discriminator over time, converging to what might happen in the data. With this in mind, we can go into our first contribution, or SHALE, for safety-aware hierarchical adversarial imitation learning for autonomous driving in urban environments. And this was joint work with Etienne Gula and Johannes Fischer from Karlsruhe Institute of Technology that started when I did a little rotation there. So to motivate this project, we note that low-level imitation learning can be really difficult, but luckily, many autonomous vehicles and other robotic systems use low-level optimization-based controllers informed by mid-level decision-making. So what might happen when you're trying to navigate through this through this roundabout is that mid-level decision-making might choose between whether to maybe stop, yield, or accelerate into this roundabout. And then that would pass parameters or make the appropriate choice of low-level controller to use to actually get through this environment. With this kind of insight in mind, our goal here is to actually learn mid-level decision-making. So it's to learn how to make that decision from only access to low-level data and potential controllers someone can use and a simulator. And in doing this, we get to use a hierarchy to ensure safety. So to do this, our approach SHALE combines hierarchical adversarial imitation learning with a layer for safety awareness. In our formulation for hierarchical adversarial imitation learning, again, given fixed, quote unquote, safe, low-level control options, often sometimes called macro actions as well, we learn a high-level option selection policy whose goal is to have trajectories come out who end up matching the data. So we're learning basically how to make these high-level decisions and let the controllers take over such that the resulting trajectories match what we see in our data sets. We combine this with safety awareness, where we then condition those high-level policies on predictions of controller safety. To do the actual imitation learning piece, we still maintain the same low-level trajectory distribution matching objective. But then we show that we can put off policy gradients to the high-level policy with discrimination rewards that are still accumulated along each option that we take. So here we're trying to learn a high-level policy that still fools a low-level trajectory discriminator. We can then take this policy that we've learned offline, combine it with predictions about the safety of controllers that we make online to form a safety-aware hierarchical controller. And the point of this, again, is to choose options from states given predictions of that option safety. So luckily, this can use many different tools for predictions of option safety, and many tools exist. So in this slide, we just visualize the methodology. So the goal is we're trying to learn parameters for a high-level policy and low-level discriminator. In our case, both of these are neural networks that we're trying to fit the parameters of. We combine that high-level policy with safety predictions to make a safe hierarchical controller. That controller interacts with a simulator that we've built to generate low-level simulated data. And we compare that data to the expert data, the true data that we get of how people actually behaved to update the parameters of our policy and our discriminator. For our experiments, we used a simulator that we built out of what's called the interaction data set of urban driving scenes, where we control the one vehicle, the ego vehicle, along its path, while other vehicles are allowed to follow their recorded tracks. So here we show metrics that display some absolute performance, as well as metrics that compare performance to maybe the experts. So for absolute metrics, we're looking at the success rate and getting across these scenarios and their travel distance. For comparisons to the experts, we're comparing the differences, like the physical differences between the trajectories, along with the velocity differences and the overall distributions of accelerations that are seen in the simulations. We do this for both in distribution scenarios and out of distribution scenarios. So ones that we also haven't seen in our training data. And that's important because in real life, it's often the case that your scenarios aren't going to be the same ones that you trained on. In fact, it's never the case. We compare against a rules-based model, a data-only model, so one that's using behavior cloning to directly regress states to actions, and a couple different models in the simulator regime, one that's just doing low-level imitation, and one that's an ablation of our hierarchical one without the actual safety predictions. And overall, we see that we're able to improve performance in both these settings. I should note as well, though, that we did this with very simple control options. So our control options were just to target a velocity after a certain point in time. Very simple predictions of other vehicle collisions. So we just forward propagate the velocities, and also very simple models of how other agents would behave based on different changes of yourself. So we expect that given good versions of all of these things, then the performance differences would be even larger. Finally, we'll show a scenario comparing the outcomes of the true expert. So that's this car in red, and this is again what's happening in real data. We'll compare this quickly against this rule-based model and shale. So in the rules-based model, what we end up seeing is that later on in this trajectory, a car appears into the intersection and the rules aren't able to overcome this, leading into a collision. Whereas in our learn model here, the safety predictions at the end kind of take over, they reset the option that's running, and that's able to make a stop to avoid that collision.
What are those curves?
Oh yeah, so for the learning-based ones, where also our features are basically LiDAR measurements to these cars in 5 planes or something like that. So yeah, great. So to summarize our first contribution, we introduced a method for learning a policy in simulation that chooses high-level control options to match low-level trajectories. To do this, we combined hierarchical adversarial imitation learning with safety predictions. And we saw in our experiments that we outperformed low-level driving imitation, even with very simple control options and collision predictions. The main limitations, or some of the limitations of this work, are that really, as a limitation of this whole area, when you're doing things in simulation, you're requiring on-accurate simulation, and therefore you're really only valid in those simulated settings, or close to those simulated settings. There are inherent shortcomings of the low-level adversarial imitation learning method that we use, namely instability in training and low dimensionality of admitted feature spaces. These are things that works since then have tried to address and can continue trying to address. There's latency of safety predictors. So if you're doing very difficult safety predictions, those have to work themselves into the simulation and into your online planning. And then in this case, in this work, we're limited to finite discrete options, also something that can be changed. Great, so that wraps up our first section. Let me take another sip of water really quickly. And then I'm gonna switch gears now to talk about our second contribution, which addresses outcome and state uncertainty using safety constraints. So to model state uncertainty in my thesis, we use partially observable Markov decision processes, or POMDPs, which augment MDPs with imperfect information. So rather than observing the true state of a system, in a POMDP, agent observations are only correlated with that true state, where that correlation is modeled through a possibly stochastic observation function. So a simple example might be a problem of deciding to feed, whether or not to feed a baby based on imperfect information on whether or not it's hungry. And you might not actually get to know whether it's hungry, but only get observations of whether or not it's crying, which you might model as being correlated to whether or not it's hungry. So you would have to simultaneously maintain a belief of whether or not it's hungry using those observations, as well as come up with a good policy for feeding that baby given a belief. A more relevant POMDP for us, and this is courtesy of Kunal and maybe the teaching team of one of the previous versions of A228, we look at robot localization. So in this robot localization problem, the states are the true position and orientation of this robot. This robot doesn't actually know where it is. Instead, it has to maintain a belief over all the possible places it can be and use its observations, which in this case are a bump sensor that just basically only tells it whether or not it's at a wall, to first localize itself and then go to that goal. So you can see every time it hits a wall, its belief changes a little bit with the information that it's getting, like information that it's at a wall. And we have to plan so that we can hit enough walls to sufficiently localize and then go to the goal. And I want to point out here that we're not like learning how to do this in simulation or something like that. We're just giving a planner our models and having them plan. One downfall of vanilla POMDPs is that they don't admit hard constraints, only maybe soft ones in the form of large negative rewards. To address this, constrained POMDP solvers or CPOMDP solvers imposed hard expected cost value budgets. So they say to find a policy that's going to maximize your rewards over time, but do so such that other constraints satisfy different cost budgets. So this can be general in that it could allow you to do things like specify states to avoid, like basically giving things high cost for getting to a bad state and saying you can never get that high cost. But it can also do things like maybe maintain budgets of different objectives over time. Here are the rough sizes of the spaces that recent constrained POMDP, CPOMDP solutions can admit. And this is really just like very approximate. Offline methods, like those based on finite state controllers or point-based methods, can handle relatively small, discrete states and low, like discrete actions and observation spaces. Now, online methods, like those based on Monte Carlo tree search, might get around this state limitation by looking at the set of reachable outcomes online. So they'd be limiting themselves, even though the state space might be continuous or just very large, they'd limit themselves to the possibilities just when they're doing online planning. With that, I'll briefly discuss my second contribution for online planning for constrained POMDPs, and specifically continuous action and observation spaces through dual ascent. And again, this was presented last year at the Conference on Automated Planning and Scheduling and his joint work with Anthony in the lab. So specifically here, we wanted to design CPOMDP planning algorithms to allow action and observation spaces to also be larger continuous, with the key insight being to sample promising actions and observations during search. So to do CPOMDP planning online, previous work, so one way to do this, so one previous work formulated the constraints into a Lagrangian, so shown here, and then solve this primal problem by interleaving Lagrangian Monte Carlo tree search and dual ascent. And I'll go into really quickly, high level, what those are. The Lagrangian tree search component says to fix those dual parameters, so lambda, and try to optimize the policy through Monte Carlo tree search, specifically through partially observable Monte Carlo planning, and using a Lagrangian action selection heuristic. What this means, for example, is that if there's a trade-off between exploring two action nodes, one that leads to high reward but is very risky, whereas one that leads to low reward but is very safe, if your current estimate for the dual parameter was low, you might say it's okay to take that risky action and explore that high reward. But if that current estimate was high, you want to focus on staying safe and exploring nodes that are safe but maybe have lower reward to them. In between searches, online constrained Monte Carlo planning would use dual ascent to then update that Lagrange multiplier as lambda. So the idea here is that if we're violating this constraint during our last search, we should maybe increase how much to care about the constraint by increasing the price on it. So our work extends this Lagrangian partially observable Monte Carlo tree search method to continuous spaces using a technique called progressive widening. So progressive widening lets us artificially limit the search tree width at different nodes of that search tree The idea is that if we're not visiting a part of the tree very often, we shouldn't expend a lot of compute trying to evaluate all the possibilities that we run into. So another way of saying this is if we visit a tree node a lot, so either a belief node or an action node, as we visit it more and more, we can increase the number of possible children that we sample from that node. This leads us to two algorithms, one where we propagate states and iteratively build beliefs, and one where we propagate those beliefs directly. I'll briefly talk about that second one, especially as it pertains to our third contribution. So in that second method, or constrained particle filter trees, we do a Lagrangian-guided belief state Monte Carlo tree search. What that means is that we're searching, instead of searching over states, we're searching over beliefs. So I said earlier in this talk, these circle nodes represent maybe states that you could be searching over. When we're doing planning under state uncertainty, oftentimes it makes sense to search over the set of states that one could be in at a particular point in time. So each one of these nodes would maybe represent one snapshot of that graphic earlier that showed all of those blue points that a robot could be in at any point in time. So we want to search over beliefs, track costs alongside rewards, explore actions with that optimistic Lagrangian heuristic, and then importantly, we want to subsample actions and belief transitions in promising areas of the search tree using progressive widening. Once we're done doing one iteration of this, we can update those Lagrange multipliers at the root node with dual ascent using the explore trajectory costs of our last trajectory sample. So in our experiments, which I'll only briefly mention in the interest of time here, we demonstrated that our methods for online planning and continuous POMDPs can get high rewards while usually satisfying constraints. However, we noticed that they have limitations. So for one, though dual ascent will guide search towards satisfaction, there are no guarantees, especially in an anytime fashion. So one thing is that we see that even in the discrete action and observation case, they're only satisfying those constraints in the limit. And we can further miss high-cost subtrees due to that progressive widening, so due to that sampling. We also see that it's ineffective in problems where coarse sampling is insufficient, and problems that might require really large, long planning horizons. So in my next section, I'll discuss how we can use hierarchies to get around some of these limitations. So in this third section, we work towards addressing these problems from the last contribution by, like we did in part one, leveraging hierarchical decomposition. This work is entitled Constrained Hierarchical Monte Carlo Belief State Planning, and it was joint work with Hugo, who I saw was here, and Kyle and Anthony as well. So to consider why hierarchies might be really useful here, you can consider this light-dark constrained POMDP. So in this problem, an agent starts with high uncertainty in its position. So it's on this 1D continuum, starting out in this maybe dark region, not really knowing where it is. It has to take either small, medium, or large steps to first localize itself in this light region, and then get back to this like final good point, this green point here, all while avoiding this red region, which would give it a penalty. So a good policy to solve this would start by taking medium steps and then small steps to first localize itself in this safe but like high visibility region. And then once it's officially localized, it would quickly go and navigate to the goal and terminate. So the problem with doing this is that doing this with particle filter trees requires a deep search, which leads to exponential blowup in the number of trajectories that we need to search across. So even if we only sampled like 1 or 2 observations under each action, with 7 actions, planning to a depth 7 requires us to get across 1 billion possible trajectories to find the right set of actions. And we need to do this early on to get a good policy. So in this work, we introduced constrained options belief tree search, which addresses this tree blowup by planning using a hierarchy. The idea here is rather than planning over low-level actions, we want to plan over options or macro actions or low-level controllers, similar like we did to the first section of this talk. Again, these are often available in robotic domains. In this search, Kobetz imagines the particle filter beliefs that would come up after each option termination. So we're going to execute one of these options, let it run until it terminates, and see what belief comes out. We want to limit the number of sampled semi-Markov belief transitions with the same techniques from the second contribution using progressive widening. So we want to only take a few possible samples of what might happen from each action that we select. It would be way too much to evaluate all of the possible things from all of the possible observations that happens for each option. And then we want to plan over this lopsided tree where the results can come out after 2 steps of executing the option, or 5 steps, or 20 steps after executing the option. In light dark, we can really get away with planning over options that either go to goal by greedily navigating the mean state to the goal, and options that use different strategies to localize. So in the search itself, we imagine different possible results of taking these options and use our imagined samples to plan accordingly. In practice, we don't really know what localized should look like, but what we can do to get around this is just template and craft a bunch of localized actions. And the cool thing is we can just have safe search, just pick the best one for us. So even if they're bad, even if they violate the constraints, we'll have search overcome those limitations. So a good policy here, we'll find the best first one to localize and localize safely, and then it'll quickly go to goal. And planning this way really reduces the size of the trees that we have to plan over. In our experiments, we demonstrate that COBET scales CPOMDP planning on 4 constrained domains with large or continuous state action observation spaces. So this spill point domain, which I think is really cool, is based on a carbon sequestration problem where one has to inject carbon into a subsurface that we really don't know a lot about. We don't know the geometry of it. We don't know maybe things like the porosity or the features of the rock. So we have to maintain a belief over possibility of all of those things, and then pick the right injection points and how to make observations so that we can safely plan, all without spilling carbon back to the surface. Doing this requires doing some picking a point to inject really early on, and so it requires doing a very deep search very early on in the problem. In our robotic domains, so similar to the robotic localization example I showed, we're trying to localize ourselves to now go to this small goal region, but we also want to do this while avoiding this hard constraint in the middle here, so avoiding a collision with this box. We see that COBET significantly outperforms the non-hierarchical baselines, which can't plan at all in the robotic domain. So in the robotic domains, they really just end up meandering in this left area because they don't want to risk the possibility of going and accidentally running into this constraint. And so here's an example with just simple options. So the options we craft are literally just go until you hit a wall, or turn and go until you hit a wall. So just with search over really simple options, we get out a good sequence of taking some localization actions before navigating to the goal while avoiding that region. COBETS also has some nice safety properties where we can track in that search, we can track the remaining cost to go and assign that cost to go to different options. So if our options can stay feasible to those constraints that are assigned to them, one thing is that this whole search can be safe anytime. So independent of the number of searches you take or a number of simulations you take in your search, you're going to come out with a safe solution. So we showed this for light dark here. So even going down to 10 searches with some pretty basic safe options that we craft, we're able to stay underneath that cost budget. So we're able to satisfy that constraint, while the non-hierarchical version only is able to satisfy constraints even with those same safe options, is only able to satisfy those constraints as you get to maybe 100 searches. Finally, we demonstrate that the reduction in tree size from a hierarchical decomposition allows COBETS to search over many options while coming up with good plans. So importantly, many more options than there are underlying actions in the problem. So here, where the underlying action space is only 7, but we're able to get good solutions out to maybe 30 when we use pretty good options, and maybe down to 20 when we're adding random options. So just options that take the same random steps for a couple of steps. I think this is really exciting because it motivates future work that if we could auto-generate some of these options, for example, by prompting LLMs or pick your favorite method, we could use something like safe search to imagine what might happen and then choose the best ones of those auto-generated options to plan. So we can maybe overcome the uncertainty about safety and auto-generate options by throwing search on top of it. So to summarize, my research problem asked, how can we impose runtime safety while planning under varied modes of uncertainty in very large problems? My contributions use novel applications of hierarchies and constraints to address planning under uncertainty in different, safe planning in different combinations of outcome state and objective uncertainty. In our first contribution, we showed how we can impose a hierarchy for safer imitation learning while using data to overcome objective uncertainty. In our second contribution, we showed how we can do online constrained POMDP planning in continuous spaces by combining Lagrangian search with progressive widening. And in our final contribution, we showed how we can leverage hierarchies to scale online constrained POMDP planning to very large problems, which we saw might also have some nice safety properties. I want to just quickly conclude while outlining maybe some open questions and areas for future work that might relate to these themes. So one big question related to the imitation learning theme is in safe generalization of data-driven decision-making. So how can we ensure that inferred objectives and learned policies can quickly transfer to scenarios outside of their training distribution? So another way of saying this is how can we get policies that were trained in Mountain View or Phoenix to go work in Berlin or Yerevan? Another question is related to constrained open loop planning. So oftentimes, this talk focused on closed loop planning. Oftentimes, open loop planning can lead to useful approximate solutions, and it can be much faster, but there doesn't seem to be a lot of work in open loop planning and continuous constrained POMDPs. Another question is, how can we do constrained planning under partial model uncertainty? So throughout this talk, I assumed that the models that we have are pretty well known and accurate, but it can often be the case that those models aren't accurate or are accurate in some states, but less accurate in others. For example, where we might be able to collect a lot of data in highways, but less data in weird edge situations or something like that. So one interesting thing would be, how do you do constrained planning while reasoning about model uncertainty? And finally, many of the recent advancements in machine learning and control have been facilitated by significant improvements in computation and hardware. So while there are many works already addressing parallelization for closed loop planning, improvements here would scale our safe planning capabilities. Great, and then I just wanted to mention that while I talked about these three works, I had the incredible opportunity to work on a lot of awesome topics, and I just wanted to end by saying thanks to all my collaborators over the years.